It's my pleasure to introduce David Blankenbeckler. So you can read the full bio, I guess, on our website, and maybe he will tell us a little bit about himself as well. But David has been with Intel for a long time, and he has been involved with the Rowhammer also for quite some time. And I think today he's going to talk about that history and also a little bit about the future. And yeah, really excited for your talk, David. So please take your time. Don't feel rushed for the delay. I think we allocated 45 minutes for this, with some Q&A maybe afterwards. So whenever you're ready, take it away.
Okay, thanks. And first, I just want to say great job by all the presenters. Really interesting work, and keep up the great work. So I have been involved with Rowhammer kind of since the beginning. And, you know, it was kind of a surprise thing for me. It wasn't like I wasn't even really working on this type of thing at the time. It was back in 2012. I had been working on memory and IO buses for the past, at that time, like 11 years, but I spent like 20 years working on memory and IO buses, and I had done some board design and system design and that kind of thing, but didn't really know much of anything about DRAMs. And I was just going about my day, and one of the senior managers called me aside and said, "Hey, we've got this big issue with DRAMs, and we need somebody to lead our technical team to go figure out what to do about it." And I was like, "Great, good luck." But yeah, actually, I decided to go ahead and take the challenge, and led the Intel team that drove our initial debug and understanding and mitigation strategy and all of that for Rowhammer back in 2012. And then, you know, after spending a year of doing that, I kind of went back to my normal job, and then kept getting called back basically every time a new major thing happened with Rowhammer. So it was always my kind of side project up until about almost a year ago now, 9 months ago, when I decided maybe I should just make this my full-time job. So I started a little memory security team at Intel. So that's what I do today. So yeah, so I really never thought I'd be working on Rowhammer, you know, in 2023. If you would have asked me in 2012, I would have thought, no way, this is going to last that long. So, but anyway, very interesting topic, and very happy to be here. So what are we going to talk about? Well, here's the legal disclaimer, which I'll let you briefly read. Okay, so what I'm going to talk about today is I'm going to give a bit of a brief history of Rowhammer back from the early days. I think that'll be pretty interesting for people to know that a lot of this has never really been outside of Intel. The story of how it was found, how it was debugged, and then some of the things that we did in the early days to mitigate Rowhammer as an industry, not just Intel, but as an industry. And then we're going to talk about where we are today. And today is kind of defined as DDR4 and DDR5. So some of it's kind of history, but you know, we're focused primarily on DDR5 and beyond at Intel, but DDR4 is widely used in the market still. And then we'll talk about kind of what's next. And I'm going to bring up, I think a lot of great work is being done, but there are a couple of areas where I think maybe we need a little bit more attention. So I'll talk a bit about that. Okay, so this is a kind of high-level roadmap, and I'll kind of talk through each of these as we go through the talk. But back in 2012, we were starting to see, actually it was even late, you know, 2011, we were starting to see unexpected memory errors in validation at Intel. We were validating whatever current product it was that we were getting ready to ship, and we started to see these unexpected memory errors. We actually started to see them from customers too, but eventually this got root cause to Rowhammer. Then in late 2012, 2013, the industry started to implement mitigations to help reduce the risk of Rowhammer. And the DRAM suppliers at that time were indicating that they were going to fix it in DDR4. So we did our mitigations for DDR3, and then I kind of went back about my business and went back to doing other things. And then in 2015, Google Project Zero folks were doing some research, and basically, by the way, up until then, we didn't realize there was even a security concern. Back in 2012, 2013, we thought it was a data integrity concern only, not a security problem. but Google showed us that wasn't the case, and actually it was actually a pretty big security concern. So we got back involved and made sure people, made sure our mitigations were effective and that kind of thing. And then again, I went back about my business, went away from Rowhammer up until 2020. And then in 2020, there was a couple of papers that came out. Trespass was the first one, and then a little later, maybe a year or so later, Blacksmith. So those, generated a bunch of new interest, and we had to do some changes in terms of our Rowhammer mitigation plans to help address that. And then we'll talk about moving forward with what we've seen on DDR5 and what we're doing beyond DDR4. So yeah, so let's go back to 2012. So I want to also kind of introduce the guy that actually root caused Rowhammer. He's somebody that I've been working with for over 20 years now, and he's a great engineer. He's one of the kind of people that has an insatiable curiosity. In fact, I talked to him recently, and I'm like, "Hey, what you been up to?" And he said he got bored and started writing his own physics engine. So he's still going at it at 70 years old. But yeah, we actually call him Rowhammer Stevens at Intel, and we actually gave him a plaque at one point and put Rowhammer Stevens on it, which I thought was kind of funny. But yeah, he's been working on memory for quite some time. He worked on his first memory controller about 45 years ago. And today he is retired, but he does do some consulting. In fact, I had him doing some consulting for me during trespass time frame. He came and worked for us for about 6 months, but he's still very sharp and very busy. So if anybody's looking for a consultant, he might want to get in touch with him. So how was it found? So in late 2011, we were seeing random DRAM errors and validation, and they were very kind of rare. I mean, we didn't see them very often, but we were seeing them, and every error we find, we try to track down and understand exactly where it's coming from, but nothing was repeatable. So it was one of those situations. It was very difficult to know what to do about, because we just randomly saw these errors and then never saw them again. But about that time, some customers started saying, "Hey, we're seeing random errors," and we said something's definitely wrong here, because we should not be seeing this. And we had one customer that had a test that was repeatable. So they said, we see errors every day, like at least a few bits every 24 hours. So we worked with them, and they sent us their code, and Roy set about looking at it. So what was that software doing? Well, it was not doing Rowhammer, at least not as we know Rowhammer today. But it was in the end result was basically it was causing Rowhammer damage. So as Roy started to look at this and understand what was going on, he found out that it had to do with multi-socket system and the caching protocol. So just before I go into the kind of the details of what happened, very quick primer on the MESI protocol. I know most companies like Intel has a variation of this, and AMD has a slightly different variation, but they're all kind of have this MESI protocol where there's 4 states or 4 or more states that a cache line would be in, and it's modified, exclusive, shared, and invalid. And hopefully people are somewhat familiar with this, but I'm going to step through relatively slowly how this worked out. So hopefully you'll kind of catch on to what was going on in this case. So if you think about the case where you have a value of 1 stored at some memory location X and DIM2, for example, and you have both CPUs trying to read the same address. So CPU 1 might read it first, and it'll read it into its cache, and it'll mark it as exclusive. It's the only, it has exclusive access to it, and it's still equal to what's in memory. Then later, CPU 2 may come along and read it as well. The snoop will see that that it's in the CPU 1 cache. So now both caches get updated to mark it shared. So everything's fine, everything's equal. 1 is in the memory, 1 is in both caches. So no problem. So as long as this is the case and it's just reading, nothing really happens, right? But what happens if one of the CPUs tries to write to the memory address? So let's take the case where CPU 1 wants to write a 2 to address X. So it would write a 2 to address X. CPU 2 cache now sees that happen and marks its cache as invalid, and then CPU 1 would be marked as modified. So memory is still 1 back in the DRAM, it's still 1, but CPU1 cache has a modified cache line, and that memory location is 2, and then CPU2 has an invalid cache line for that location. So now what happens if CPU2 tries to read that address X? Well, memory is wrong at this point, so it'll try to do the read to address X, but it was marked invalid, so it's a cache miss. And then with the cache agent, it would basically snoop CPU1, which shows it's modified. So the correct data comes over from CPU1, updates the CPU2 cache, and the key thing here is it gets written to memory. So you see a memory write occurs. So that's the main thing to notice there is that you have this write back to memory. So what happens if CPU1 is continuously writing to address X, and at the same time CPU2 is trying to read address X? So you can kind of see as CPU1 writes, it causes reads. Every time it writes, CPU2 is trying to read it, and it causes this behavior where you have these write backs happening to memory. That's basically Rowhammer. So this was essentially what was happening. It was actually a little bit more complicated than this, but the code that was showing bit flips about a few every 24 hours was doing something like this. And Roy was able to figure that out and say, at the end of the day, what was happening was a lot of write backs were happening. And he said, hey, what if I simplify that? Oh, by the way, I wanted to also call out some recent work in this kind of area, OEC Prime, where they looked at a similar type of impact and had some ideas on how to mitigate it. So Roy noticed these frequent accesses were occurring, and he said, I can simplify that. So he simplified it down to kind of the well-known Rowhammer case. Yeah, I think he was actually doing writes at the time. He used them move into TQ instead of reading and cache flushing. But this is kind of the well-known case where he's just flipping between two different rows to cause the page to close. Although I think actually in the case he had, it was actually closed page mode, so he didn't necessarily have to do that. And now he's getting, instead of a few bit flips every day, he's getting bit flips every second. So that was kind of where he resolved it down to Rowhammer. And I was trying to research actually where the name Rowhammer came from. We definitely called it Rowhammer back then, but I kind of vaguely remember that the name came from well before then, maybe even the 70s, but I was never able to find that. So if anybody knows that during the Q&A session, if you could let me know where the Rowhammer terminology actually came from or originated from. But then Roy thought, what if I hammer both sides, both sides of the victim row? And then he started getting hundreds and even thousands of bit flips per second. So this was way back. This was a long time ago, back in Q1 of 2012, when Double Hammer was born. So we were like, uh-oh, this is not good. This is a major issue. And we wanted to understand just how prevalent it was. So we set out to understand this by looking across a wide variety of DRAMs. And we looked at older material back to 5x nanometer all the way up to 2x nanometer DRAMs across all the suppliers. And we found kind of a surprising result that basically when they went from planar to 3D with the 3x nanometer generation, Rowhammer became a big issue. And as we saw it happening with our Rowhammer code on about 70% of the material, and with 2x it was even greater than 70% of the material. So this was a kind of massive issue for us and for the industry. But the first thing that came about when I remember vividly, talking to the DRAM suppliers at the time, and pretty much all of them said the same thing. Why would anybody do that? Like, why would you, try to avoid the cache and take a performance hit and have code that actually, does Rowhammer? Because again, we thought it was just a data integrity problem. We didn't think it was a security issue at that time. So we went out to understand, is this a real world case or is it just a test case? And we looked at a bunch of different workloads across client and server. And these are some of the worst ones that we found. So on the left is the hammer threshold, the number of disturbs before you get a bit flip. And at the time, the DDR3 DRAMs were basically good up to about 150,000 hammers or disturbs. And you can see there was many workloads that were exceeding that, both on server and client. So So yes, this was definitely a real world problem. It was not just a test case or, you know, some obscure thing. So what did we do about it? So we had, it was kind of the best kept secret in the industry, I would say. We had a large consortium, all the DRAM suppliers and all the major OEMs worked together to work on ways to mitigate this. Everybody was under NDA. It was kept quite secret at the time. And we came up with some ideas to mitigate it, which I'll walk through. And then again, for DDR4, the DRAMs, we're going to fix it internally. So for DDR3, just to kind of summarize the what we actually did about it, there were two things. Two big things from the industry point of view. One was the DRAM vendors improved their devices through screening and some other internal changes they made to get about double the threshold. So going from 150 to say 300K. And then Intel and other OEMs as well added options to increase the refresh rate. So you could go from standard, you know, refresh rate to 2x refresh rate, or I think we even had options for like 1.5x, and depending on the risk, et cetera. And then the other thing that Intel did was add pseudo target row refresh, which I'll talk a bit more about that. But this was an idea that we came up with in 2012, and got a patent on that and implemented that in many of our products. And then again, DDR4, the DRAMs were going to handle it internally. And so we eventually ended up dropping pseudo TRR, kind of unfortunately, because then we needed to add it back. But it was in quite a few of the client products up until recently, and then the later DDR4 products dropped it, and then we ended up adding it back for DDR5. So let's talk a bit about refresh rate. And this is a diagram that we use sometimes internally when we talk about Rowhammer and explain what Rowhammer is to people. But and everybody here I think is quite familiar with Rowhammer. But the basic idea is you have an aggressor row doing a lot of activates, and you have a victim row. And every time you do an activate, the victim loses a little bit of charge. And if you do enough activates before a refresh, it may drop below the threshold. And then when you do the refresh, it's going to kind of yank it to the opposite state. So that's, you know, basic Rowhammer. But you can kind of, the reason I use this slide is just because if you see that if you double the refresh rate, then your refresh is happening over here somewhere. It's less likely, you know, to drop below the threshold before you get a chance to do a refresh. So it's a great mitigation for Rowhammer from a, you know, effectiveness point of view. But the problem is it impacts performance, and as the raw kind of underlying Rowhammer threshold decreases, you can't keep increasing refresh rate forever. But yeah, the biggest thing is the performance impact and the power impact. So we can't just keep increasing refresh rate. So that in combination with what the DRAM suppliers changed in their designs gets us up to, you know, an effective mitigation. So you can do one or the other, and you get to like 2x, which is almost good enough, where you can see most workloads were below the threshold here. But if you do both, if you go to 2x refresh and the DRAM improvements, then you're well above what we found in commercial software at about 600K. And again, just want to reiterate, at this point in time, we only thought that Rowhammer was a data integrity problem. We didn't really consider it to be a security problem. So the other thing that we did was what we call pseudo target row refresh. And this was the novel screen scheme that we implemented in our memory controllers to help reduce exposure. One thing that we looked at early on was maybe we need to track row activations and keep a large table and understand who's getting the most row activations and take care of those. But that's not very practical from an implementation point of view. It's not scalable, you know, it has a lot of issues. So we came up with this idea: what if we randomly select addresses and insert dummy reads essentially to the adjacent rows? So that's what we did. And so basically every memory transaction, there's a probability that the memory controller will select that address, and then it'll put that into a queue for insertion. And then it'll do basically dummy reads to the plus or minus 1 rows. And then this is kind of tunable because you can just basically turn up and down the kind of insertion rate or the injection rate to hit whatever quality goals you have. And we believe this is a great approach. Two key things you have to consider is that your selection method needs to be random enough to avoid, some kind of detection or reverse engineering. But the biggest one, and the one that we have spent the most effort on over the years, is the next one. For this to work, the memory controller has to know where the adjacent rows are in the DRAM, and it's well published at this point. I mean, we figured this out in 2012, but there are what we call swizzling inside the DRAM. So it's not always a direct one-to-one translation between the logical address and the physical, adjacency inside the DRAM. So we have to account for that when we do these dummy reads. We have to calculate the actual physically, adjacent row and make sure we're actually, fixing the victim. And that's been a challenge ever since we introduced pseudo-TR, keeping up with that. We try our best to, to stay in touch with the DRAM suppliers and for them to let us know when they change things, but it's difficult to do that. So yeah, that's been a problem. And we actually had a solution for this even way back then. This is a bit of history now, but everybody uses the word TRR for in DRAM, protection for Rowhammer at this point in time. But the original TRR term actually came from Intel, and it was target row refresh, and it was actually a command that would solve this whole problem of that we had with pseudo TRR, where the memory controller has to determine the physically adjacent row. With TRR, we could do the same thing. For example, we could have done a similar thing where we randomly selected a row for mitigation, and then we would do a TRR command to tell the DRAM to take this aggressor and and take care of the victims. But again, this was for DDR4, and at that time, the DRAM suppliers decided they were going to fix it in the DRAM instead, so this got removed from the spec. But it actually comes back sort of in a different way with directed RFM, which I'll talk a bit about in a few moments. Okay, so then again, we were thinking data integrity problem, not security problem. But then in 2015, Google did some excellent research and did their paper showing that you could do privilege escalation. So this was a big surprise. In fact, I remember, I was not a security person at all back then, and back before 2015. But I remember in 2012, 2013, going to every security person I could find, because I had it, I kind of was worried that, is this a security problem? So I went and said, is there any way to take advantage of this? And I talked to as many people as I knew. And even at that point, McAfee was part of Intel. So I went to McAfee people and talked to them. And everybody said, no, we don't really think it's a security problem. But it turns out we were wrong there. And Google showed that it indeed was a security problem. So this basically, for us, it created a renewed interest in Rowhammer, and it definitely created a ton of renewed interest in Rowhammer in the academic world. But we were moving to DDR4 at the time, and DDR4 was fixed. And so we basically reiterated all the things that we told people to do already, like increasing refresh rate and using pseudo TRR and all of that stuff. And then went about our business and kind of forgot about Rowhammer again. So that brings us to today, and today means DDR4, basically the last 5 years. So yeah, in 2020, I was again surprised. I was had honestly kind of forgotten about Rowhammer, working on completely different things, and the trespass paper came out. So that was a bit of a surprise. I mean, we always kind of, I would say, knew that it was not a fully defensible solution in the DRAM because there wasn't enough time to properly do it, I would say. But we kind of assumed that they were doing something like we did with pseudo TR that was quite random and was not detectable. But it turns out it wasn't quite as random as we thought, and people were able to show that you could use creative methods to kind of get around the schemes that they were doing to take care of victims. So yeah, great work by both of these papers. So where are we today? So with DDR5, we have a couple of several new features in the spec that I think are important to help with Rowhammer. We've got refresh management. We have adaptive refresh management, which is kind of a way to throttle refresh management, and then we have directed refresh management. And I'm going to talk about each one of these briefly, just in case you're not familiar with those. And then, of course, we'll have additional improvements in DDR6 and LPDDR6. So just briefly, refresh management. So, normally DRAMs do their internal mitigations during the refresh command. And of course, we could do more refresh commands, go to 2x refresh, but that impacts power and performance. So to avoid that, the new command, the refresh management command, is similar to refresh, but it's only issued when you have a lot of activates to, for example, to a bank. You could do these extra RFM commands to give the memory controller additional time to do their mitigations. So the way this works is essentially during boot, the BIOS will read the mode registers in the DRAM. There's RFM thresholds stored there. You'll copy those over into a table in the memory controller. And then during runtime, the memory controller is going about its business and doing activates to banks. And then every time you get a bank activation, it increases the counter for that bank. So there's, you may have every bank may have a counter, and every time you access the bank, it increases it. And you can kind of see what happens over time. You actually can, when you do a refresh, you can kind of reduce your count for that bank, and then you can reduce it a lot when you get an RFM. So, yeah, so every time when you do the RFM, basically you get a chance to do a big decrement of the act counter for that bank. And then when the DRAM gets the RFM command, it has additional time to go off and mitigate rows that are impacted by prior activates. So the question is RFM enough? And unfortunately, I don't think it is. So a couple of issues that I see with it. One is that it still relies on a single line of obfuscation defense. The DRAM mitigation schemes are not defensible and they're not transparent, right? I think this is well known. We don't know what they do. We've reverse engineered a lot of it. People have gotten around them, but you're relying on that one line of defense, and it's if you get around it, then giving them more time to do that thing, it's not going to help. The next thing is that it's not scalable. So as the tolerance goes down, you're doing these activate counts at the bank level. I mean, you could maybe do them at lower levels, but it's not efficient. So you're going to have unnecessary extra RFMs for the bank. So as you get lower and lower thresholds for these bank counters, then you're going to start to get more and more performance impact. And then the last one is basically adoption challenges. It's an optional feature for the DRAM. It's actually a required feature for the memory controller if the DRAM says they require it. But the problem is that DRAM vendors so far have not required RFM, so it's not being used. So if it's not being used, it's not helping. So the next one to talk about is directed refresh management. So this is a kind of a combination of pseudo TRR and RFM. At least that's how we think about it at Intel anyway. But similar to pseudo TRR, the CPU decides which aggressor row to select for mitigation. And again, I would say this is another level, kind of a secondary defense in depth kind of feature, not the primary mitigation. Unlike pseudo TR, the victims of the aggressor row are calculated by the DRAM. So this is the big issue we've always had with pseudo TR, is that the complexity of relying on undocumented, internal DRAM implementation, and having the memory controller have to know how to do the proper remapping to make sure that we're actually hitting the correct victim row. So directed RFM solves that problem. And then, like pseudo TR, the memory controller would track rows. It could do it in different ways. It could do. It's not really, just like I mentioned before, it's not really practical to do it where we're tracking all the frequently activated rows. And there's been many different, proposals on how to do that more efficiently. But it could be done in some way, and it could be done probabilistically or in, just in some way. But there's never. I don't think it's practical to have a guarantee that a row will be mitigated before a bit flip occurs. So that's why I call it a secondary kind of line of defense. So the way this works, basically, there's every time you do an activate to a bank, you have some algorithm, could be probabilistic, or it could be some counting algorithm inside the memory controller. And then at some time, the tracking logic in the memory controller determines time to do a mitigation for a specific row. So it would inform the DRAM. There's a couple ways this is done. It could do a pre-charge with the DRFM bit asserted. This will tell the DRAM to latch that row for later mitigation. So it stores that row in a DRFM latch in the DRAM. And then sometime later, the memory controller would send the DRFM command and wait, basically, to give the DRAM time to do the mitigation. And then the DRAM would actually calculate the victim rows and do the mitigation. And it actually does have bounded refresh or blast radius as well. So it can mitigate, up to ±4 if it's supported and if it's configured that way. Okay, so what's next? So let's talk about where we are and where we're headed. So one key thing is that the industry's definitely aware that Rowhammer is still a problem and is still working to reduce the risk of it. As I said, I kind of treated Rowhammer as a part-time thing up until recently, and now it's my full-time role focused on Rowhammer and memory security more generally. JEDEC, definitely plays a big role here. The challenge, I would say problem even with JEDEC is it's getting a whole bunch of various people to agree on something to move forward. So that's always a very slow process. Personally, I think where we really need more urgency is from the people that buy DRAMs, the people that the big players that really buy tons of DRAMs. I would love to see them drive a lot more urgency to kind of finally fix Rowhammer. That would be the OEMs, the cloud service providers, people like that really control the money. They're the ones that will get this moving faster. So one idea that has actually been around for quite some time is NDRAM tracking of activates by row. So, as we all know, starting with DDR4, the DRAM started to mitigate Rowhammer internally, but the schemes they have, they're not really defensible. They don't precisely keep track of activates at the row level. And we've seen that clever access patterns can circumvent the protection. NDRAM tracking can solve this problem. It was actually first proposed way back in 2013 by Kuljit Bains and Bill Nell at Intel. And then more recently, it was kind of expanded with the Panopticon work. But it basically requires that the DRAM allocate some DRAM array space to track the precise activates per row. And the obvious initial problem with this is the cost, right? It's going to increase the die size a bit. But personally, I'd love to see. That was why I kind of mentioned I really would like to see the cloud service providers and OEMs and the industry to get on board with something like this and be willing to pay for it, because I think the cost won't really be that much. And if everybody does it, there's no no disincentive, I guess, for people not to adopt it. But the way this works is, basically during runtime, you activate to a certain row, and that row, every row, but that particular row has a counter at the end that gets incremented. And then if the count exceeds a certain threshold that's set by the DRAM, then that row is placed in a queue for mitigation. So later on, when you get a refresh to the DRAM or an RFM command is sent, mitigation's done. So every time you do a refresh, the DRAM has an opportunity to look through its mitigation queue, and if it has time, it can start to mitigate the victims. And then there may be also cases where the DRAM may get full. I mean, the DRAM queue may get full. So a scheme like this could have a provision for an alert or some signal back to the memory controller to say, hold off, my mitigation queue is full, and send me more RFM commands. So it can basically say, alert, hold off, and then the DRAM controller would start to send RFM commands until the DRAM has done enough mitigations. Okay, so thinking kind of beyond Rowhammer, or I would say even beyond what I've seen the focus today, even around Rowhammer, there's a couple of areas that I think need a bit more focus. One is around confidential computing, and I'll briefly describe what confidential computing is in a moment. And then the second one is DRAM security improvements. So let's talk about confidential computing. So confidential computing has kind of gained a lot of interest in the past few years to provide protected, encrypted memory environments, so that, like at a cloud service provider, a tenant, for example, could have a VM that it feels very confident is in a protected space that nobody can access, not the cloud service provider or another VM or anyone, right? They want to feel very confident that their assets and their code and their data is all well protected. So the concept is for Intel, we have SGX, and then we have a new feature called TDX, Trust Domain Extensions, which has recently been released on Sapphire Rapids. And one of the kind of, I guess, challenges with all of this is that the trust boundary is quite limited. So with these kinds of technologies, you're saying that there's many things that are untrusted, and you don't have to worry about those things. And if you think about that, that's a pretty big statement. So just to give an example, if you're saying that memory is going to be protected and you don't trust, for example, the BIOS, how do you do that? I mean, BIOS actually brings up the memory. BIOS could do many things that could compromise the security of the memory. I mean, some simple things, for example, is that BIOS could set it up so that you have aliasing, so that there's different memory, different addresses that go to the same memory. So that's one of the key challenges. And obviously, we fixed that one. I mean, that one's we've architected it so that that's not possible. But those are the kinds of things that you have to think about. So we did some work recently last year with Google to look at trust domain extensions in particular. It was a joint security review, and there was a couple of examples that came out of that I wanted to briefly talk about related to Rowhammer. And you can also learn more about this. There's a YouTube video, Chips and Salsa, that talked about it, and they published a paper, and we published a paper as well about this. But the two things that I wanted to bring up that came out of that were related to Rowhammer. One was there was a register they identified that could be used to turn off ECC. So, this is a server product, has ECC. So a malicious BIOS could potentially turn off ECC, and that was just straight up a miss. We found, this was an unexpected one that we didn't think would turn off ECC, that kind of thing. But we obviously fixed the ones that were obvious, but there was one that they found that we missed. And then the other one was some refresh settings. And we actually kind of knew about that, but it was a late find, and then we ended up, they found it as well. So we ended up fixing that as well before product launch. But the basic idea was with Rowhammer, refresh rate definitely matters. And they could, a malicious BIOS could play with the refresh settings to slow down refresh rate, for example, and make Rowhammer attacks much more likely. So that's just to give you some ideas about the kinds of things that, when you don't trust, for example, the BIOS, things that you have to look out for from a security point of view. So we expect there'll be more research in these kinds of areas related to confidential compute. And, we welcome people to please let us know if they find something. The other area that I think needs a lot more attention is there's not a security mindset, I would say, in the JEDEC specifications, at least not for DDR. If you look at the spec now, you can see there's runtime mode registers that there's meant to be accessed during runtime, but they also have fields in the same registers that should not be accessible during runtime. There was one, for example, that we found recently that had a DRAM test mode in the same register that you're using. I think it was for ECS or something. I forget the exact one, but it was definitely meant to be used during runtime. But in that same register, there was another register or another field that that was a reserve pin that was for some test mode or something. Fortunately, that one didn't do any harm. But the point is that you should not have that, right? You should not have test mode registers in the same, or fields in the same register as something that you're meant to access at runtime. The other one is the sideband bus is insecure. So this is one, as we worked on confidential compute, we realized some of the challenges with making sure that everything was legitimately set up, is that the I2C bus that you use to talk to the SPD on the DRAM, on the DIMM, is not really considered secure. It's untrusted. You know, it's outside the trust boundary, because anybody can read it, and you could even design a board that spoofs it. So there's, you know, it's not really a trusted bus. So we'd like to see that improved as well in future specs. So I think the new DRAM specs really should look to address these things. Better mode register partitioning. You know, we need to have security policies around the mode registers, and we need to have a secure sideband bus. And again, these are really important in a trusted execution environment. So just kind of to summarize, that I want to, you know, thank all the, you know, academic research that's happening. I think that's necessary to keep the industry on their toes about Rowhammer. So keep up the great work there. The next one is computational compute. I think is a emerging technology that probably hasn't had as much attention as it needs to have. So consider that, and when you're looking at you know, at your research projects, I think there's some great opportunities there to help improve the security of computational compute. And then as well, looking at the actual DRAM specs and see if there's other security, I would say, lapses in the specs where we can improve those going forward, like you know, like the things that I mentioned. Okay, so will Rowhammer ever be in the rear view? I asked that to ChatGPT and Bard, and all it could do is give me a haiku. I thought they did a pretty good job. Okay, so that's it. So I'll just put this up here just to kind of show the roadmap of what we talked about. But yeah, now I'll open it up for questions.
Wow, great. Thank you so much, David. Let me click clap button. Yeah, that was really nice. Thank you so much for the for this keynote. I hope people have questions. I have maybe one. Oh no, there's a question already. More questions from Kevin. He was first. Go ahead, Kevin.
Hi, David. Thank you for giving the talk. It was really interesting, and I appreciated it. I had a question about kind of the observation of the coherence-induced hammering in 2012. So it would appear that kind of the write-backs caused by Messi were identified as a factor back then, but I haven't. When I did work on this, I was working post 2020 on Skylake servers that came out later, and I'm wondering, what was the motivation behind like retaining roughly the very similar coherency setup in that scenario? And in fact, subsequently, I think there was a memory directory which added extra coherence traffic.
I am not a cache coherency expert, so I learned more about that just getting ready for this presentation than I knew before. So I don't know if I can really answer that, but I do know that it changes over time, and I think it's quite different now than what it was back then. I think it was like Ivy Town. I can't even remember what product it was, but yeah, every generation we do different tweaks to improve and make it more efficient and so forth. But yeah, I don't know if I can answer your question though.
Thank you.
Yes, thank you. Kaveh, yeah, go ahead. Next question.
All right. So thanks a lot for the great keynote. I really like the technical stuff. So Intel has been working now on Rowhammer since 2012. Now it's 2023, and Rowhammer is still a problem. So if you could go back to 2012, knowing what you know now, what would you do differently?
Yeah, I would have pushed harder to do the you know, perfect tracking, as we called it. Basically Rowhammer, you know, activate tracking by row, and just done more to try to force the industry just to go ahead and eat it at that point in time and implement the proper fix on DDR4. But yeah, it's much easier said than done. But that, if we would have done that, we wouldn't be sitting here today talking about Rowhammer.
Thanks. So maybe another question. Do you think that perfect tracking alone is enough?
That's a good question. The problem, yeah, the challenge, I guess, with perfect tracking is you start to think about blast radius and the scalability of it and questions like that. I think it'll get us. It's way better than what we have today. It'll probably get us until we transition to new technology, but yeah, I don't know. That's an area that probably needs more research.
Thanks.
All right, we have another question from Stefan, and also there was one online, but maybe Stefan, go ahead.
Hi, David. Thank you for your talk. It's impressive to hear how Intel has had a first seat to Rowhammer for over a decade now. I was wondering if Intel is aware of any forms of DRAM disturbance other than Rowhammer, and if they can share that with us.
There's an interesting paper coming next week that's kind of Rowhammer and kind of not. I would recommend everybody to pay attention to that one at ISCA. But other than Rowhammer, for DRAMs, not really. I mean, it's all somehow related to Rowhammer.
Thanks.
Okay, there was a question online from Moin. Awesome talk. Enjoyed learning the history and insights. What are your thoughts on non-local hammering, such as done by Google half-double paper recently?
I was initially a big skeptic. I mean, we actually worked with Google on that early before the paper even came out. But when they told me that originally, I was really skeptical that it was even real, but was honestly a bit surprised that it was real. But yeah, I definitely believe it's a problem. And that's how the spec got changed. You know, that basically was why the bounded refresh got into the JEDEC spec for DRFM. And I know the DRAM suppliers are aware of it as well. They'll be handling blast radius and their mitigations. So yeah, that was good work and definitely has an impact, positive impact on our mitigation strategies.
All right, Young-Ho, you have a question?
Yeah, excellent talk. So what's your personal view about the right distribution in job between the CPU and memory over time in the future to deal with the Rowhammer? I mean, you once mentioned that. Okay, so you once mentioned that which RFM is not ideal in some sense, and then you suggested something that basically CPU or memory controller does most of the things. And from time to time, DRAM vendors say that it's better for DRAM to do almost everything to deal with the Rowhammer. What is the right balance between?
My opinion is the DRAM definitely should do everything to deal with Rowhammer. There's no question there in my mind. The problem is that they're not. So we have to have these other features like pseudo TRR or directed RFM because there's it's kind of a, you know, who's going to go first and take a performance penalty or a cost penalty kind of a problem. One DRAM may say, hey, we're going to do perfect tracking at the row level, but then they take a 5%, you know, die size impact or something like that. So if they're the only ones doing it, obviously they're not going to do it. Or, you know, so that's why, in my opinion, the biggest, you know, the biggest stick in all of this to make things happen faster is the people that buy lots of DRAMs. And until they demand a fix, it's hard for a fix to happen because of competitive nature of DRAMs. And, you know, it's very cost conscious and it's hard for any one DRAM supplier to want to spend more money than their competitors on fixing it, unless people are going to pay for it. But yeah, all the schemes in the memory controller are supplemental in my mind. They're all like defense in depth in case what's happening in the DRAM is not enough.
Okay, thank you.
Right, one more question online from Barbara. What percentage of Rowhammer failures can be caught with ECC?
So that's I don't know about percentages, but ECC I think is pretty effective against Rowhammer. You know, I know Lucian, he actually works for me now, but he did the ECC exploit paper and showed that there was ways to get around ECC with Rowhammer. That was on client ECC. Server class ECC is much stronger. We've looked at this internally quite a bit, and we actually have some, new improvements, I would say, coming in the future that I think will help further. I can't really talk much more about, but related to ECC and Rowhammer coverage. But the key thing is about ECC is whether it's detectable, right? So for a single bit in single device kind of errors, you get correction. Then it comes down to what gets detected versus what's silent. And the work that we've done shows that the ratio there is pretty good. You're going to be extremely likely to see a detected uncorrectable error before you get silent data corruption. So I would say that from that point of view, it's quite strong. If you have a case where, like confidential computing, for example, where you could pre-characterize, or where you have additional access to the system, either physically or through a malicious BIOS or something like that, where you can manipulate that ratio, then or do some pre-characterization and find out where the silent data corruption is, then it changes the story a little bit. But for standard security, standard system, standard setup, where everything's kind of trusted, I think ECC is great protection, at least to detect it. You could have denial of service, but you'll at least detect that bits are getting flipped.
Yes. I have one last question for you. So you've been working on this for over a decade now. In 2012, you started, I guess, maybe earlier even.
Radically, but yes.
So in 10 years from now, are you still going to be working on Rowhammer, or will the team no longer exist?
I'm going to probably be sailing on my sailboat somewhere, not working in 10 years. But yeah, will other people be working on Rowhammer? I hope not, to be honest. I think there's more practical things to do, and I'm hoping that this problem is well solved by then. So, but yeah, it's probably likely that there'll be still some Rowhammer work going on in 10 years, unfortunately.
Maybe I see a consultant gig coming up for you. All right. Let's see in chat. Question, right? So yeah, thank you again, David, for the great talk.